Okay, welcome back to Essential Perturbation Theory and Asymptotic Analysis. I wanted to bring up an error or a typo that we had in the proof of the last theorem, the proof of the asymptotic expansion involved in the method of stationary phase. So I think we discovered this midway through, and I was a little afraid to admit that it was a typo or an error. I found the source of the typo or the error. Let's call it an error. So I committed the cardinal sin of copying out of another book, or at least, translating out of another book. So Marsden and Hoffman, where I got this theorem from, or whose theorem I was following, actually had the same error in there, but it fixes itself because it's a double error. So the error was in the change of variables. I had f divided by this derivative.
You're not sharing.
Oh, why am I not sharing the screen? Okay. There we go. Okay, so this error in this proof, the one that I was following from Marsden and Hoffman, appears in both of ours. So one copied the other, I guess. So this was the offensive area. It should have been f divided by the derivative of the inverse function, which is clear if you do the change of variables from this formula. So t should be equal to w inverse of x, and then you take t dx equals the derivative of the inverse function. And then, of course, you just solve for dt and you get it immediately. Okay, so that should have been there. All right, and then the next error was in this computation. I had the reciprocal of this, so that was wrong. I had alpha over 2, but then it fixed it because I had the reciprocal error in the other part, and it came out that we got the correct answer. Okay, so and everyone knows what the correct answer is for the steepest descent. And of course, we derived it heuristically, so we knew what the target was. The other error was a smaller one. This here, and I guess I still haven't fixed it. Thought I did. I fixed it in the notes, but this should just be a prime. Okay, so that's the regular function w derivative and evaluated at t naught. Okay. Okay, so if you fix those two errors, I think the proof holds together everywhere else. 2 or 3 errors, let's be honest. Okay, so let's go back then to chapter 4, which is where we want to start working. So all of chapter 4 is geared towards convincing you that the tools we're going to use are familiar, I guess, or making them familiar to you. So we want to do asymptotic expansions of a certain type of integral, and we're going to use something called the method of steepest descent. The method of steepest descent can be sometimes called the method of steepest descents with an S on the end, because you do take multiple descent paths. So the method of steepest descent can be broken into 2 flavors. One where you use what's called a saddle point method, and one where you use a connection method. So there's another section at the end of this chapter called the saddle point method, but that's essentially still just the steepest descent method. It's not anything new. But the problem is those methods use contour integrations, and I wanted to show you what contour integration is. So I kind of got carried away. And I wanted to do like 2 pages, and in the end I did 15 pages. So that's just me. So we went over contour integration in the plane for real functions. We argued that it can be written in a vector format, which is kind of useful. We talked about simply connected sets and convex sets. We said that every convex set is simply connected. That's and basically every disk, is a convex set, and then is therefore simply connected. So if you want to think about these sets that I'm talking about as just being a disk, that's fine, usually. We talked about Green's theorem. I think we maybe have ended on Green's theorem. So Green's theorem is a way of translating an integral around a boundary, special kind of integral around the boundary, right? Contour integration, and transfers it into an integral over the domain that is bounded by that contour. So this contour we called gamma, and the domain we called d gamma. Okay, so this is Green's theorem. And the contour in this case has to go in the anti-clockwise or counterclockwise direction. All right, how many of you have seen Green's theorem before? Okay, good, everybody. Most calculus courses have, they're dropping the vector calculus portion, and some people are missing out on these things now. So this is where I ended last time, talking about complex contour integration. So the idea is this: we're given a open bounded set. This one doesn't have to be simply connected or anything like that, but we're going to think about a set that looks like this in the complex plane. And inside of that, we have a contour which connects points. Didn't mean to make it smooth like that, but that's okay. Oh, then it disappeared on me. So you have a point Z1, the starting point, and a Z2, and a contour connecting these points. So you also have a function f, which is defined on this set D, and it has to just be continuous in this case for things to work. We're going to assume that the gamma connecting points Z1 and Z2 is smooth, although we could make that, oh my goodness, there we go. Settle down there. There we go. So gamma is smooth. We could make it piecewise smooth as well, as I said before. So what does it mean for gamma to be smooth? A curve that maps an interval. We can think about this as time. That's convenient. Into a complex plane. What do we mean for that to be, or a set in the complex plane? What do we mean for that to be a smooth curve? Well, we mean if it was a real curve, then it would be a smooth function, okay, in the usual sense, right? So if it was real, then it would be some alpha of t, beta of t, right, which maps into the plane. And so those functions would have to be smooth functions. And now, of course, you really don't need smooth functions. It might be enough to be C1, something that, a curve that you could take its derivative. And maybe the derivative is continuous. But in any case, this just means it's nice. Then the complex contour integral of f along gamma, which is denoted like this, is defined as this. So this is the notation, and this is the thing that defines that notation. If you want to compute the integral from Z1 to Z2, you have to have this parameterization. This is also called a parameterization of a curve. So sometimes the curve is just the trace of this object, and sometimes the curve really denotes how you parameterize it. So we won't make a distinction usually there. Now this object should, this might puzzle you a little bit, but it is well-defined object. So what we do is we take f, and we're going to evaluate it along the path. That means we plug in these values for gamma and we multiply that by gamma prime. All right, so this is complex multiplication. And so at the end of the day, you have an integral over a real domain, a to b, but you're integrating a complex object, which I could break into its real and imaginary parts. And so basically boil it down to real integrals. And I'm going to show you how to do that. Now, I get a little bit technical here, so please forgive me. So some people gloss over this sort of stuff, and but I wanted to make it a little bit fancier. Suppose the idea is here, suppose I have a complex or a set in the complex plane, and I'm going to call that D. And I have a curve in the complex plane called gamma. Now, usually we do not put a bold on the gamma when it's mapping into the complex plane, but we did make it a vector when we mapped into R2, right? Now, in some sense, there's no difference between mapping which maps from AB into the complex, a set of complex numbers, and a vector which maps into R2. But we're going to make a distinction between those two so that we don't get lost in translation. So suppose we have a set and a function that's defined on that set, and we're going to have also a complex contour that's at least continuous. Then the realification of this complex set is what we denote by dr2, and that's exactly the same set, but it's in R2 rather than the complex plane. So it's the set of points x and y such that the point x plus iy is in D. Does that make sense to everyone? So this set here lives in the complex plane. And we have another set that I can now it's exactly the same by the magic of copying, which lives in R2. This set here is not called D anymore. We're going to call it D of R2. Okay, but they're exactly the same set in some sense. The curve, instead of giving it the name gamma, we're going to give it whenever we refer to it in the real sense, we're going to give it a gamma with an arrow over it, okay? And we'll call that the realification. The real part of F is denoted U, and that maps D from R2. D of R2 says that's the realification set into R. And the imaginary part of F, V, which maps that same set into R, are functions that are defined via this relation here. Okay, so F is a function of a complex variable and actually maps into a complex plane. So we're going to separate out the value of F after I do this mapping into a real and imaginary part. But we're going to imagine that U takes variables from this realification set D, and also V takes points from the realification set and maps them into R. All right. At the end of the day, these values are just real values once you put the points in. Another notation that we're going to use is that U of xy is equal to R. So this just means the real part of F. And V of xy equals I of F. That's the imaginary part of F. And similarly, as I said before, if we have a complex contour that is defined via its complex parameterizations, A of t and B of t, or alpha of t and beta of t, then the realification of that is a vector, okay, a vector mapping, which takes t and it maps it to a vector, and the vector is alpha t, beta t.
That's a typo.
Okay, where's the typo?
Well, clearly, E should be capital.
Okay. Is it spelled correctly otherwise? Okay, good. Okay. You know, sometimes in English we stop capitalizing a word after a while. Yeah, if it gets into such common use, then the name is forgotten. But I agree. I don't think this is one of those cases. But I don't know about like the Cartesian plane, probably still capital C. Okay. Well, I made that statement and I don't have any good good examples to back it up. So does anybody?
I think you see that stuff both ways a lot. I mean, I agree with you after reading a lot of this stuff over the years, you know, you see people drop the capital and you see a lot of people keep it on
Yeah,
for the same thing.
right.
I don't know which is-
Yeah. There's no police officer policing this. I guess you could do whatever you want. It's the Wild West. Well, Abner and I wrote a book, and when you send it off to copy editing, then they have a set of rules that they obey strictly. And the rules are different as to whether or not it's publication. So it's by Cambridge University Press. So they have a different set of rules for American English than they do for British English than they do for Canadian and Australian English. So interesting. But then there is a set of rules that are followed strictly. Suppose that D is an open set in the complex plane and F is a continuous function from D to C with real part U and imaginary part V. Suppose that gamma is a complex contour. We'll make it smooth to make things simple. Suppose that alpha is the real part of gamma and beta is the real part of, or the imaginary part of gamma. And this bolded. So by the way, on paper, I'll write this as gamma with an arrow above it. But in the typeset, I use a boldface. So boldface simply means vector. So then gamma is the realification of that, right? So it maps AB into the real set R2 in R2. So let's define a couple of vector functions, S and T. S is going to be U and minus V, and T is going to be V and U. Okay, so these are vector functions. They map points from R2 into R2. So I'm trying to convert this complex integration into something real that we can then apply all our theory from the real variable theory. Then the complex contour integral can be expressed in the following terms. Of course, this is what we want to define. And we have a good definition of it. It's given here. And what the proposition says is that actually you can rewrite this as a real integral, namely this one, plus I times another real integral. And in fact, I can write this in very compact notation. This is just going to be the integral from A to B of that S vector function dotted with the gamma, the realification derivative, plus I times the integral of the T vector defined up here, dotted with the gamma prime vector, the realification path. All right, so maybe this isn't clear to you, but the proof is much easier to remember than the actual formula. So all you do is you take F and you're going to multiply it times gamma, and you'll see that what you get is exactly these two functions. So remember, F can be written as its real and imaginary parts, and so can gamma prime. And if I multiply those two things together, right? So here's F, and here is gamma prime. Now you have to remember the rules of complex multiplication. Everything multiplies together the same as if the parts were real. So you can FOIL it out. The only thing that you have to worry about is whenever you see an I squared, you change it to minus I. Or minus 1, sorry. So what we get is when we do all that, at the end of the day, we should just get this. Okay, you can check the details. I have them here. I've already got it separated into the real and imaginary parts. Remember what S was? S was U and minus V. So that's that. And there's gamma prime. And what was t? T was u, or no, actually t was v and u. So you just have to reverse the orders there, and you just get this. So therefore, I've shown that this is equal to this and plus that. Okay, two real integrals which are joined with this complex unit. Where did this guy come from? Well, this was shown before to just be this. And this guy here was shown before just to be this in the real setting. So we don't have to bother with that. Questions about that? Just conversion of a complex thing that maybe looks complicated to you all, if you've never had complex analysis before, into something real, which is quite simple. Yeah, and I've already said that, so we can drop these guys. Okay, so complex integration obeys, because you've seen how to translate this into real integration. It obeys certain linearity properties, and so here they are. So if I have any functions that are at least continuous, defined on an open set, and I have a bunch of contours, gamma, gamma 1, gamma 2, that are continuous, and let's say piecewise smooth curves. Suppose that C1 and C2 are arbitrary constants, then we have this linearity property for the integral. The integral of C1 times F plus C2 times G is just C1 times the integral of F plus C2 times the integral of G. If I integrate over a contour and a negative contour, what that means is I'm basically running this contour in reverse. Then that's equal to minus the contour of the minus the integral of the function over the original contour. So this just means minus contour just means run that contour in reverse. That's the definition. So if a contour is from AB into C, then the way you're going to run the minus contour is it's going to be run exactly with, well, you can define it like this. We want to start at B, right? And we want to end at A. So minus a contour is going to run things in reverse. And if I integrate over the sum of two contours, so what this means is if I have a contour which runs from Z1 to Z2, and then another contour which goes on to Z3, we can call this gamma 1 and gamma 2, then the sum contour just means running them both one right after another. Okay, so that's what this contour means. And that can be split up into a contour integral over gamma 1 and a contour integral over gamma 2. That makes sense, I think. Okay, so basically you just run it up to here, that's gamma 1, and then you run it up to here, that's gamma 2. You add the results together, and this is what you get. All right, I'm not going to prove that one because that one just follows because we know that we can translate this into real contour integrals, and real contour integrals have this property. Questions? So no proof required, really. All right, so this one's about a reparameterization of a contour. Suppose that D is an open bounded set and F is a continuous function. Suppose that gamma is our contour. We could imagine that to be our first contour. It's a smooth complex contour, and eta is another contour. So this one, actually, this is another function, sorry. Eta is a function which maps CD into AB, okay, in a smooth monotonic sense. So actually, it's going to be this guy that's going to be the new contour. This chi contour is defined as gamma composed with eta. So that means we've got to make sure that eta of C is equal to A and eta of D is equal to B, because we want to map this interval here exactly into this interval in such a way as it keeps the order correct, okay? This function, therefore, has to be smooth and monotonically increasing, okay? So it's basically it's basically a way of taking this contour and either stretching it or contracting it, but you do it in such a way that this eta is monotonically increasing. Now we're going to define a new contour chi, which is gamma composed with eta. So this is what we call a reparameterization curve. So the theorem is that, or the proposition is that if you integrate f over gamma, then that's exactly the same as integrating over the same parameterization. The reason is you're covering the same amount of territory. You're really covering exactly the same contour. So why should the parameterization matter? Well, the good news is it doesn't, and that's because parameterization doesn't matter even in the real sense, and we can convert everything. So let gamma bold and chi bold be the realifications of gamma and chi respectively. By the definition, on one hand, we're going to have this, right? That's for gamma curve. What about for the chi curve? For the chi curve, I have this. But now you realize chi is just a composition of gamma and eta. And so when I take the derivative of that, I get chi prime and an eta prime. And same here. I'm sorry, I think I said chi prime. It's gamma prime, eta prime. Gamma prime, eta prime. Now, by the real change of variables formula from real land, this guy is just equal to this, okay, because of real change of variables. And same here, because of real change of variables formula. Remember, we're allowed to change variables when we do regular integrations. And the change of variable formulas are exactly as you know them, right? Well, since they're valid, then we can go backwards and get to here. But of course, this is just equal to the regular integral. This is just equal to f of z dz. Okay? So we can change variables. Something else that we're going to use a fair amount is that, these estimates. So these estimates apply to contour integration in the same way that they would apply to regular integration theory. If f is a continuous function and gamma is a continuous piecewise smooth curve, and suppose that f is a bounded function, or has this bound for all z and d, then whenever I integrate from or on gamma of f of dz, then I can bound this by the largest value of f along that curve or along the set, which is going to be m, times the length of the curve. And that all makes sense, right? Because that's exactly the same thing for a real integral. If I take the absolute value of the integral from a to b of f of x dx, and f has bound m, then this is less than or equal to m times b minus a. Okay, so that's familiar to us from real land, and it holds also in contour land as well. Now, the length of the contour is defined like this. Okay, it's just the integral from a to b of the absolute value of gamma prime dt. More generally, we have this theorem, or this result. This just fills in all the details in an exact way. So I can move this, this is actually a modulus, right? Because this contour integration is complex valued. So this is modulus, and it comes inside, hits this guy, and it hits this guy whenever I convert this to what it is. And then this can be replaced by m, taken out of the integral. And then we're just integrating something in real land. The modulus of gamma prime of t is just a real thing. Yes, question.
Silly question. The difference between modulus and the absolute value, it's sometimes, is it like, sometimes, but it's a perfect definition that I can.
Oh, sure. Yeah. So, so if I have a complex number, okay, then I can no longer take the absolute value of this. So we define something called the complex modulus. And the modulus is defined in the following way. It's equal to the square root of a squared plus b squared. So if you view z as a point in the plane, then it's exactly the Euclidean distance between the origin and the point z. Now that modulus obeys almost all of the same sort of properties that you would expect from the absolute value. Like, for example, if I take the modulus of two numbers, z and w, complex, then that's equal to the modulus of z times the modulus of w. So it obeys a lot of the same principles. But you have to use something more sophisticated when you're talking about the absolute value in quote of a complex number. Any other questions about, so please, that's why I'm doing this review of complex contour integration, because I know that some of you haven't seen too much about complex numbers before. So slow me down if you need to ask any questions. That was a good question. All right, now, again, when we're integrating it from this point, I can pull that. This is a real integral now, because the modulus is always a real number, if you see, right? It's always in fact, it's a non-negative real number. So now here, this is just a real integral. This guy is bounded above by m. It can come out. And then I'm just integrating this, and that's the definition of the length of my contour. Okay, the modulus of the contour is the length of the contour. All right, so now contour integration is related. Well, it's important for everything in complex analysis, really. And we're going to relate this to analytic functions. But I need to tell you what an analytic function is first. All right, so derivatives of complex functions are more or less the same as the derivative of real valued functions. So if f is a function defined on an open set in the complex plane, we say that f is complex differentiable at z naught if and only if the following limit exists and is finite. So if this limit exists and is finite, that's the same sort of limit that you see, or the same limit process you see when you take a derivative of a real valued function, right? The difference here is that, well, let me explain the difference momentarily. So if this limit exists, then we call that limit the derivative of f at z naught, and we give it that symbol. If it's differentiable at every point inside of D, then we say that f is complex analytic in D. All right, some people use it, you have to be careful, because the word complex analytic means something different to different people. Okay, so I'm using it in a, so this isn't, so the way I'm using it is, I think, the most widely adopted way. When you say that something is differentiable, you can say it's complex analytic, but other people use different words for this, okay? Holomorphic is a common one. Okay, so how many of you have heard of holomorphic before? Is that more widely used? Calvin, in the complex analysis that you're taking right now,
They flip it.
okay.
They use having in the neighborhood of the point having a convergent power series is
Okay, all right.
They flip it.
So they flip it, yeah. So yeah, a lot of authors will use this term instead. I find this term to be strange. I'm not sure where it comes from. Does anyone know where it comes from? What's the etymology of that? So morphic means sameness or change. So holomorphic, I'm not sure.
What is hole? I
Mhm.
rarely use this prefix.
I don't know.
I think
Maybe.
that electromagnetic fields inside of the hole when the fields come out from like generates
Uh-huh.
that cylinder, what it creates, it's actually kind of something which blows. I don't know, that cylindrical thing with the you see the nuclear power plant shape of the nuclear power plant outside,
Uh-huh.
that's the holomorphic kind of shape, which is that it doesn't try to convert to the center and you
Uh-huh.
it's kind of have that kind of
Hyperbolic.
yeah.
I-
Hollow means entire whole, so like, for example, a hologram is like.
Oh, okay. So holomorphic, so again, what was hollow? What's the
Entire or
ent-
whole.
entire, but then adding it to morph. Okay. All right, cool. So, now,
Have a certain niceness of shape in order to have these properties.
yeah, I mean, to be complex differentiable requires a little bit more than, real differentiable. That's true.
Do you try to listen to the ChatGPT explanations?
Sure, let's hear the
So-
ChatGPT explanation.
So holomorphic, hole means whole and entire. In particular, we know that in complex analysis, a function, if it is one-time differentiable, is infinitely many time differentiable because the power
Yeah.
series has the same radius of
Right.
conversion every time differentiated. So the whole means in this way, like is like the property holds for the
Yeah.
whole series of like the
So then I would say don't use this term because the surprise comes later that if it's differentiable once, it's always differentiable, right? So I don't know. I think I spilled the beans there. So it turns out if you're complex differentiable, then that is a very powerful statement. And that's because limits and limit process in the complex plane is different than on the real line. For this limit to exist, it has to exist for h coming to 0 from every possible direction. Okay, and so that makes the fact that this holds a little bit more complicated. Okay, and it gives it more structure, more power.
It's an extremely strong.
It's a strong condition, yeah. To say this is much stronger than saying the difference quotient has a limit on the real line.
If a function is differentiable on everywhere and also bounded, it must be a constant. Like that's a new booster. Well, we don't have that in
Right.
theorems.
Yeah.
That's only happening in complex.
Exactly. All right. I'm going to state this without proof. Those of you taking complex analysis have seen it before, but it's a very powerful and useful statement. Suppose that we have F defined on an open set and it has real parts U and V as usual. That's my common notation. F, if I write F, then U and V are its real and imaginary parts. Suppose that F prime exists at the point Z naught, which can be written as X naught plus I Y naught in D. All right. Oh, I'm sorry, I stated that wrong. So then F prime exists at that point, D, if and only if U and V are differentiable in the real variable sense at X naught, Y naught in D and satisfy the Cauchy-Riemann equations. Namely, du dx is equal to dv dy at that point. And also du dy at that point is equal to minus dv dx at that point. So if the function is complex differentiable at z naught, then it's true if and only if u and v, its real and imaginary parts, are differentiable in the real variable sense and satisfy this Cauchy-Riemann equation. If it turns out that u and v are a bit smoother, that means their derivatives are continuous functions. Yes.
Have you explicitly defined C1 or C infinity?
No, that's something I think that I have assumed throughout, but here's what it means. So if so let's go to one-dimensional sense. So if I say that a function is in C1, from A, B to R, that means it's a function. And it takes A, B into R. And it's a continuous function. So sometimes we write continuous here. I don't know if you can see that, but. And its derivative exists everywhere on A, B. And it maps continuously into R as well. So that's what it means to be C1. If it's C2, then it means that these two things hold, plus the second derivative is a function that is well-defined, exists, and maps continuously into R. It's a continuous function. All right, so that's what it would mean if I said C2. If I say C infinity, it means that all derivatives of all orders are continuous. All derivatives of all orders are continuous. So, and that's what it means to be a smooth function. Smooth function means that every derivative that you want to take exists and is continuous. Polynomials, for example, are smooth functions. The sine function, the cosine function are smooth functions. The square root or the absolute value function is not a C1 function, right? It has a problem here, right here. It's not differentiable at that point. So there are plenty of functions that we're interested in talk about which aren't smooth, but most of the ones we talk about will be smooth. Does that answer your question? Okay. I think the notation is fairly common, but you may not have seen it if you're in physics or engineering as much. All right, so by the way, how many of you have seen this notation before? Okay, so some have, some haven't. Okay, it's good that we got that definition out of the way. Probably should throw that in the appendix somewhere or something like that. Or actually, maybe I do. Maybe it is in the appendix, but thanks for asking that question. Now, if U and V are C1 functions and satisfy the Cauchy-Riemann equations, then F is complex analytic on D, and we actually have a derivative formula for F. So the derivative of F at Z is equal to the partial derivative of U with respect to X plus I times the partial derivative of V with respect to X. We also have another formula which also works, and that is the derivative of V with respect to Y minus the derivative of U with respect to Y, both evaluated at X naught and Y naught. Okay, we'll demonstrate this through an example, but we're not going to prove this. This is a rather famous result. Most of the time, the Cauchy-Riemann theorem is, or the Cauchy-Riemann theorem is stated by expressing the Cauchy-Riemann equations. But the theorem is much more powerful than that. Again, it says that F is differentiable at Z naught if and only if X and Y, or U and V are differentiable at X naught, Y naught. Okay. And these things are satisfied. So it's a much more powerful statement. All right. So we're going to use this as well. We're going to use all of this stuff. I promise you, we're going to use every bit of it when we talk about the steepest descent method and the saddle point method. So suppose that D is an open set and F is a function. And I actually should have said that, well, let's see, do we need it? I thought maybe I should say that F is analytic, but let's see. Okay, so suppose that F has the real part U and the imaginary part U. If U and V are C2 functions, then U and V are harmonic on D, the realification set DR. And what we mean by a harmonic function is that if you take the second derivative with respect to X plus the second derivative with respect to Y, you get 0. And the same with V. If you take the second derivative with respect to X of V and the second derivative with respect to Y of V, that equals 0. That's what it means to be harmonic. So the real and the imaginary parts of F are harmonic. Now, why is F itself an analytic function? Well, that's because U and V are very smooth functions, okay? So if you go back to the theorem, if U and V are differentiable in the real variable sense, well, we have much more than differentiable, right? We have that they're C2, which means that their derivative exists. The first derivative exists, the second derivative exists, and both are continuous functions. So that's a much more powerful statement than just saying that the derivative exists. So that means that F must be harmonic, right? At all points in D. And because it's C2, we have that, I'm sorry, I said harmonic, I meant to say analytic. So F has to be analytic. U and V are harmonic because of, well, this is the definition. And the reason that they're harmonic is because of the Cauchy-Riemann equation. So the Cauchy-Riemann equations guarantee that U and V are differentiable functions. Actually, that's not the way we want to use that, because we're already assuming this, and F is analytic. F is not assumed to be analytic. So, but what we know is if these are the real and imaginary parts of an analytic function, which they are, since U and V are C2 functions, then the Cauchy-Riemann theorem does kick in, and we know that the Cauchy-Riemann equations have to be satisfied. Okay, now, if we know that these functions U and V are C2, then there's something you learned in advanced calculus, if you took it, and that is that you can interchange the orders of differentiation. Okay, does everyone remember hearing about this? You may not have heard about this in an analysis class. You may have just always assumed it all your life. But in your vector calculus class, whenever you learned it, you needed to have a U and V being smooth enough so this happens. If they're not smooth enough, then this may or may not happen. Even if the second derivatives exist, if they're not continuous, then you may not have this interchangeability property.
I think you also need to have an open name at the particular point that you're talking about.
An open neighborhood?
Yeah, you know. Otherwise, you can't even talk about the derivative.
Yeah, I mean, I'm in an open set to begin with, so
Oh,
I think we're okay there. What's that? Oh, okay. Yeah, and I believe you need the C2. If it's just differentiable, then you don't necessarily get it. And of course, I need it to be second differentiable because I need to take a second derivative. Now you can just use Cauchy-Riemann, right? And replace these derivatives in a certain way, and you can show that you can get this harmonic formula. Okay, so I'll leave that detail up to you guys. Thought about giving it as a homework assignment, but it's a very simple one. Okay, so now we know that if F is analytic, and it has the real and imaginary parts U and V, then this U and V satisfies the Cauchy-Riemann equations. And if they're smoother than that, if they're C2 functions, then in fact they're harmonic. So we call them, in this case, we call them harmonic conjugates, okay? U and V are sometimes called conjugates for, I'm not sure what reason, but U and V are called the conjugates of F. And if they're smooth enough, then they're called harmonic conjugates because they satisfy these equations, okay? This is what it means for a function that's in R2 to be harmonic. Okay, so harmonic conjugates. All right, let's do an example. We've done enough babbling with not any computation, so let's do some computations. So suppose that D is a bounded open set in the complex plane as usual. DR2 is its realification. I'm just going to say D from now on. You guys understand that set is the translation into R2. Some people just use the same set. Okay. And I don't blame him for that because it's annoying to say. Okay, so let's define u to be x squared minus y squared and v to be 2xy. Then these are harmonic conjugates, it turns out. To see this, let's consider the following f. Suppose that f is equal to z squared. So this is the most famous example of this, and so many of you have seen this before. So if I write z as x plus iy and then I square it, so squaring works the same way in complex land as it does in real land. You just multiply a number times itself, and then you just use the rule that whenever I get I squared, I have -1. You get an I squared on the y term, so you get x squared minus y squared. That's why this whole thing becomes the real part. And the imaginary part is anything that multiplies the I, so that's going to be 2 times xy, and so there are your real and imaginary parts. Now, both of these turn out to be C2 functions in certain domains. You have to be a little bit careful about where you are, but okay, so we're going to, let's see, so is this true on any, I'm trying to think if this is true on any open domain. Let's see. I guess so, yeah, it is. So these are still, these will be C2 functions on any domain that we want in the plane. It only remains to check that this function is analytic on D. So here's how we can check that it's analytic. We can check this via the Cauchy-Riemann theorem. So if you check at any point, dx dy is equal to 2x, and that's equal to dv dy. If you don't want to prove that it's analytic by taking it a derivative, this is the easy way, okay? Now, there are little theorems that said any polynomial in Z is analytic already. So this is just showing it via Cauchy-Riemann. So the Cauchy-Riemann equations hold, okay? Du dx equals dv dy and du dy equals minus dv dx. Okay, so if you calculate those derivatives, you'll get these common values. All right, and we know that these are C2 functions, so that we know that they're going to be harmonic as well. By the way, what's the complex derivative of z squared? If you didn't learn it already, complex differentiation obeys the power rule, obeys the quotient rule, obeys all the usual rules of differentiation. So we know that this should turn out to be 2 times z, but we can use the Cauchy-Riemann theorem to prove that. So we have two versions or two derivative formulas for using the Cauchy, using the conjugate harmonic conjugates, u and v. So the first one involving u and v is just this one, which works out to be 2z. And the second one also gives 2z. So either way you slice it, this is a harmonic function, and the value of the derivative is 2z anywhere you compute it. Any questions about that? Okay. Now this is a contour plot of these harmonic conjugates. And this one here, let's see, which one did we have as yeah. So these contours here, let me get my blue. These are the contours of constant v, constant values of v. So I believe it's basically something like v equals 1, or sorry, c equals 1. So a contour plot means this. So if we take v, x, y, set it equal to some value c, those are sometimes called the level curves of the contours. I should probably use the term level curve rather than a contour, because we're going to use the term contour for something else. But I hope that there's not too much confusion. If I say a contour plot, that's the same as a level curve plot. All right, so this is like taking c equals, don't want that. This is like taking c equals 1, then 2. So it's basically, it's getting higher and steeper as I go in this direction, right? So V is getting, the values of V are getting bigger and bigger. So if I think about V as being a surface, then this direction goes up the surface. So notice something interesting about this, that these are the ISO contours, or the level curves of U. And notice that they have this orthogonality property with the contours of V. In fact, we can show that these are always going to be perpendicular to each other. And these level curves of constant value of U are the steepest ascent curves, if I go in this direction, for climbing up this mountain of V. So the blue curves are the constant contours of V. They keep going up and up. So this is going in the up direction for V. But I'm plotting over top of that these constant contours of U. And if you follow the constant contours of U, these are the paths of steepest ascent. I'm getting larger and larger values of V. Conversely, if I come down in this direction, these are the paths of steepest descent. Okay, now it depends on where I am, of course. You can think about this as being a hill which has a curve to it. The steepest descent in a certain point, it may be like this, and the steepest descent at another point might be like this. Okay, so those are 2 points that I want you to see just by this plot, that these contours seem to intersect the contours of the level curves, I should call them, of constant U, intersect the contours of, or the level curves of constant V orthogonally. All right. So yeah, I'm going to try not to use the word contour when I'm talking about level curves, but here's what I mean by a level curve. All right, suppose that D is an open bounded set and U is a function from D to R. So this is in R2. For each value of R in the range, does everyone know what a range is? You've got a domain and a range for a function. A range is the possible values of the function. Then we're going to set CUR to be the set of points X and Y in D such that U of X and Y is equal to R, right? So that's what's called an isocontour, or a level curve. So if I have a function of X and Y, let's say, let me see if I can draw my best function here. Some people are good at drawing saddle points. I'm not so great at that. I can draw a paraboloid pretty well. Actually, that should be dotted, right? All right, so suppose that I have a function like this. It's a surface. U of X and Y is equal to, if you put in X and Y, you get some number out, R, okay? So what we're looking is for places where R is constant, but X and Y are changing. So this might be the value of R here. So in this paraboloid, that would be a curve which looks like that, right? That's constant R. But we're looking for those points in the XY plane. So we have to come down to the XY plane. And so that's the contour, or the level curve, U of XY equals R. Does everyone get that concept? All right, so this is called a level curve, or an isocontour of U. And we say that it's smooth of class CK. That means it has a certain number of derivatives. If there is a curve, gamma, that is of CK smoothness from AB into R2, such that for some interval I, gamma maps I into the contour. So basically what this means is, if I have a curve which represents a contour of some function, let's say like that, we're going to say that that's a smooth of a certain class as long as there's a gamma that maps into that, and gamma has that smoothness property. Okay. Now, this curve doesn't have to be closed like that. It could be something like the curves that we saw on the last plot. So this curve because I can overlay that with a parameterization, which is smooth, then we call that a smooth curve or a CK curve, whatever the continuity happens to be. So here you can see that this curve is pretty smooth, right? And if I just draw a circle, that might be my D. Everything inside of there is a smooth curve, okay? It's of class at least CK, where K is any number. So we call that a smooth curve. So all we're interested in here is, can we trace out these curves with a smooth curve gamma? Okay, so I need to have different definitions here, right? So I call this a curve and this is a level curve. It's a little bit confusing, but I hope that it at least makes some sense. Are there any questions about that? Okay. So this is the proof that those level curves of the harmonic conjugates are orthogonal to each other. And again, it's like almost everything, it seems like we just use Cauchy-Riemann over and over again. All right, suppose I have a function that's analytic in D with nice, with these real and imaginary parts U and V. Suppose that for the point x naught, y naught in D, we have u of x naught, y naught equal to r, and u v of x naught, y naught equal to s naught. If the level curves CU R naught and CV S naught are smooth, so these are the level curves generated here according to this prescription. There's two level curves now involved here. So there's one associated to V and one associated to U. Okay, so this would be CU R naught, and this one would be CV S naught. So at this point, U has the value R naught, and V has the value S naught. They're different values for their level curves. If the level curves are smooth enough, then they have to intersect orthogonally at this point. So this angle that we have here is a 90-degree angle. So how do we prove that? The curves intersect clearly because I made them intersect, right? Okay, so both level curves contain the point x naught, y naught. So what we're going to do is we're going to compute tangent vectors of these guys, right? How do I compute the tangent vectors? Why?
Change the point, right? They hit the point.
No, they hit the point. They go through this point in the plane x naught, y naught. So remember, these are the level curves. They're descriptive of the value. So you have to kind of project up to see the value R naught and S naught. Okay.
Yeah, level set is a free image.
Yes. Yes. Okay. So they both contain this point. So I'm going to calculate their tangents here. And the reason I can calculate the tangent vector is because I know that both of these are smooth and they both have a parameterization. Okay. So what are the parameterizations I want to use? There are functions gamma and chi. Okay, they can be from different intervals in time, it doesn't matter. Okay, such that gamma maps 1-to-1 onto this curve. So that's gamma's curve. And chi maps 1-to-1 on this curve. Okay, so there are unique points in those intervals of time where the gamma curve and the chi curve intersect, right? They have to intersect at this point. Now that might be different points in their time intervals. We could synchronize them to make them the same if we wanted to. We're allowed to synchronize. So gamma T naught is equal to x naught, y naught, and chi T1 is equal to x naught, y naught. They cross at that point. We don't know what direction they're going. We didn't say that, but they cross, okay? Now, since U of gamma T is equal to R naught for all T by the chain rule, right? It's equal to, if I plug in gamma's value or the gamma curve, because as Calvin said, it's the pre-image of R naught. So if I plug this value into u, I'm always going to get r naught. So now what I'm going to do is I'm going to take the derivative of this guy. I know that the derivative has to be equal to 0 with respect to time because it's a constant in time. And what I get is the gradient, because I have to use a chain rule. I have to use a vector chain rule, okay? So I have to take the gradient of u, and then I have to take the derivative of the thing inside. Well, that's a vector, so I have to take its derivative, ordinary derivative with respect to time, and I have to dot them together. Vector chain rule, does everyone remember hearing about that? Well, that's 0. I also know that if I put in chi into the v function, that's a preimage of s naught, and so that's equal to, that's always equal to s naught. Therefore, if I take the time derivative, I get 0 again. But I'm going to carry out the derivative, and I use the chain rule, vector chain rule, take the gradient of v, and I dot that with the derivative of chi. Now, by the Cauchy-Riemann theorem, it's easy to see that these two gradients have to dot to 0. Okay, that's if you follow Cauchy-Riemann, you'll see that. So the only possibility then, if these two guys are perpendicular, is that these two vectors also have to be perpendicular. Okay. So it might take a little picture to draw that out and see it, but that's the case. Well, actually, let's do that picture. So we have these two contours which are crossing. That's not a good crossing because we know that it's going to be perpendicular. All right, so first of all, what do we know about taking a gradient at a level curve? It's going to be perpendicular to that level curve, right? And so that's the gradient with respect to this curve. So maybe I should use different colors here. That would be helpful. So if I take the gradient of the blue curve, or the gradient of the function, and evaluate it at the blue curve, it's going to be perpendicular, right? And for the black curve, take the gradient. I get that. Well, I know that this is perpendicular already to this vector. And this one's perpendicular to this vector. If they're mutually perpendicular to each other, right? Then these two vectors also have to be perpendicular to each other. There's no other alternative. So this is what I get. But then you remember the fact from calculus that the derivative of any parameterization gives you a tangent vector. And so the two tangent vectors are perpendicular. And so the level curves are orthogonal. All right, so how much time do we have? 8 minutes. Anybody need to stretch? Okay, take a stretch if you need a stretch. I'll take a drink. All right, fundamental theorem of calculus not only applies to real integrals, but also complex integrals, and that's because it applies to real integrals. So let's see how this works. For some reason, I changed notation from functions which are lowercase f to capital F. I'm not sure why I did that, but I was following Marsden and Hoffman, and maybe they made the switch as well.
Because capital F is a primitive.
True.
Usually.
Yes, in this case, yes. But I used it also, no, that's okay here. Right. No, here. No, that's okay. Yeah, I think I only used it in the sense of primitives. Although maybe not here. No, here's as well. Okay, yeah, that's why I did it. Or that's why Marsden and Hoffman did it. I'm following their treatment. Okay, suppose that f is a C1 function. So this one is this is the fundamental theorem for contour integrals of the real type. Okay, so f is a function from an open set in R2 into R1, and it's a C1 function. Assume that gamma is a real smooth planar curve in D, then you can show that we're going to prove that the path integral of gradient f of x dot dx is equal to f evaluated at gamma b minus f evaluated at gamma, sorry, this should be gamma a, right? B minus a. So how do we prove this? So this is an easy application of standard fundamental theorem of calculus, in case you've never seen it before. So this integral is defined like this. All right. And of course, we can use our chain rule, right? This is just the perfect derivative with respect to t of f of gamma t, right? That's chain rule right there. But now this is a perfect derivative of f. And so we can integrate this exactly. And so we get f of gamma b minus f of gamma a. Okay? Fundamental theorem of calculus in the standard sense. So let's do the same for contour integrals. No surprise here that the integral of f prime should be f gamma b minus f gamma a. So let's see how this works. We already proved that this would be equal to these real integrals, right? Where s is equal to capital U minus capital V, and t is equal to capital V, capital U, where capital U and capital V are the real and imaginary parts of f prime. Because this is just an ordinary contour integral. So we transform it to these real integrals, but now we know exactly what we do, or what we need to do. Okay, using Cauchy-Riemann, I thought was simpler than this, but I forgot my own proof, okay? Using Cauchy-Riemann theorem, we know that u is equal to du dx and v is equal to du dy. That's because f is complex analytic, right? And so we know what Cauchy-Riemann equations say. Okay, where u is the real part of f and little v is the imaginary part of f, and v is equal to v dv dx and u is equal to dv dy, okay? That's because of these relations here, right? I said capital U was the real part of f prime. So we know that we have a derivative formula for that, remember? And v is the imaginary part of f prime. We have a formula for that. Okay, I forget exactly what the formulas were. They're back in equations 12 and 13, wherever the heck those are. But remember, we had two formulas for the derivative of f. Okay, so at the end of the day, we can write s as being equal to the gradient of u. Okay, because of these two formulas here, gradient u, we need this guy and that guy with a minus sign. So, yep, I'm good. Gradient u, and t is gradient of v. Remember, to do that formula that we want to apply, this guy here, we need to get these things down to something which looks like that. Okay, so that's what we're aiming at. All right, so this is finally gradient of u, gradient v, and so that means that f from this formula can be written as the derivative of u, full derivative of u, and the second one here, because we transformed this t to the gradient of v, is just the time derivative of v of gamma. Okay, and now by the standard fundamental theorem of calculus for real integrals, we're done. Okay. All right, so I'm going to stop there. We're all tired of just this pages on pages of definitions and theorems and stuff like that. So I promise there are some more computations, or there are some more example computations coming where we put this stuff to the test. Like, for example, can you actually do a contour integral in the plane? You know, what does that look like? So we'll do one of those. We'll do a couple of those. And then finally, we're going to start applying this to the method of steepest descent. So that's in the next slide deck. That slide deck is also available on Canvas and should be up to date.
You
Question.
have an also typo, the.
Where's-
Should be f of z to minus f of z.
Okay.
One.
I'm getting there. Oh, there we go. Thank you. All right, I'll see you guys next time. Have a good one.